Our next speaker is Joydeep Biswas. The title of the talk is Reading the Dirt, Learning What Matters and What Doesn't for Off-Road Navigation. Joydeep Biswas is an associate professor in the Department of Computer Science at the University of Texas at Austin. His research spans perception and planning for long-term autonomy, and with the goal of achieving robust autonomy in open-world settings and with arbitrary user requests and preferences. Professor Biswas is a recipient of the NSF Career Award, the Amazon Research Award, and JP Morgan Faculty Research Award. He serves as a trustee of the RoboCup Federation and an executive counselor for AAAI.
Cool. Thanks for the introduction, and thanks for having me here. So I want to talk today a little bit about what matters and what doesn't for off-road navigation, and I want to right off the bat first quickly thank all of my collaborators. On the left are all the awesome students who've actually helped make most of this happen. And on the right are other faculty and researchers who have been excited to collaborate with to make a lot of this happen. Okay. So to set the stage, I want to actually play a video. We went to R2C2 at Grace's quarters last year to actually do some data collection. And this is not an environment that I've been in before. I knew nothing about what this environment was going to look like. I had some idea that there was going to be forests, and I knew that we were going to drive this Warthog, right? This is not a vehicle that I've driven before, so I was not allowed to drive it. I'm pretty sure I could have driven it if Christian would allow me to, but I was watching Christian drive this robot, right? And I'm going to play this video, and you'll see what's going on, right? All right, so that seems simple enough, but let me just pause there and actually point out a few interesting things. So I didn't fully expect that there'll be like fallen logs all over the place. So first of all, in this forest, there are so many fallen logs. If you're just going to avoid fallen logs, you're not going to get anywhere, okay? Secondly, I didn't fully appreciate like the dynamics of the system, the fact that there's like an independent left and right suspension, and then they rock independently. And what Christian was doing over here, if you watch carefully, is like he's slowing down, and he's approaching the log perpendicular head-on just to make sure when you cross it, it's actually not going to get stranded in between. So it'll get stranded if you try to take it at an angle. It'll get stranded if the log is too high. There's lots of ways of failing, right? Now, I wasn't trained to expect this in this environment, but within a few minutes of seeing what Christian was doing, I'm pretty confident I could have taken over the controls and actually repeated what he was doing, right? Now, the thing is, how can we actually get robots to do this? How can we actually teach robots when and how to negotiate such arbitrary scenarios when navigating in open world settings, okay? So we do a lot of work with robots, thankfully in the outdoor environments. I'm not attracting Byron's ire by running them indoors. I do a lot of indoor robots as well, a little bit, only a little bit of his ire. Anyway. We work a lot on things in urban environments. We deploy them in trails. We've been doing a lot of work in urban environments without any maps. And that's a fascinating problem because it seems like, okay, I'm just going to talk a little bit about this problem. It seems like a lot of your problems should be solved using geometry, but actually it's not. So here's a setting where it's actually going to take a curb cut ramp off, and it's going to take a curb cut ramp on again. And no two curb cuts are exactly the same, and you might be tempted to think about, I can work out the geometry for all of this and pre-program this. We've tried it. We've spent many, many hours trying to figure out what is the right threshold for the ramp and like this much and that much that the robot can handle. You can't do it. You cannot write a single set of numbers which will actually handle arbitrary settings, right? So even the geometry settings are actually really hard in unstructured environments, okay? So I want to come back to this log traversal scenario and actually just point out some ideas of what comes to mind when you're looking at this scenario, okay? So what matters and what doesn't? So first of all, what matters is that there's a fallen log. It's a long, significant, but surmountable obstacle. The vehicle must drive over it head-on and slowly to avoid getting stuck. What doesn't matter is the color of the log doesn't really matter too much, right? The dappled sunlight, it's all over the place, don't care, right? The tufts of grass in the distance, I don't think that matters in this scenario, right? And also if the robot were slightly to the left or to the right, as long as along the log, it should be fine. So I'm listing these because these are some examples of perception, features or planning and control features which are of relevance. And the first set are what we would call, sorry about that, what you might think of as the discriminative features, the things to pay attention to. And these other features are what you might call, in ML parlance, the nuisance features, things which are not really the things that you want to pay attention to. So how could we teach robots when and how to negotiate arbitrary scenarios? Well, by learning what matters and what doesn't, right? Okay, so to set the stage, what I'm going to do is that I'm going to operate in this regime for all the things that I'll be talking about today. They're going to follow this regime where we have input, some images, and it could be sparse depth as well. You're going to convert them into some learned representation. And in everything that we do nowadays, we actually don't necessarily have a discrete representation. It's actually usually a learned and continuous representation. And the reason for that is very simple. We don't know what we need to capture in the world, so we want to learn that from the demonstrations and from the environment as much as possible. From there, we go to a preference-based consistent cost in a cost map or a reward map, depending on how you see the world. And over that, you can actually do classical planning, you can do model predictive control, you can use MPPI, all of the stuff that Byron was talking about, okay? Now, the real question is, how do you actually learn this FVIS, this function which takes your perception, transforms them into these learned representations, and how do you go from there to the costs, okay? So I'll try to be a little bit more formal. So you have input some images, and you can either think of them as patches or entire images. We're passing them through these, this vision representation, which is giving us some representation Z. I'm showing them as a vector, but it doesn't need to be. And there's actually good reasons for it not to be a vector. I'll talk about that later. And eventually, you're going to get to a cost function, right? It is worth thinking about where does this image come from? And this is going to be important for the structure. Byron, thanks for raising the point about the structure of the problem. So images are are arising from an unknown observation function, and this observation function is dictated by the entities in the world, right, and the world conditions. Okay, this is rather important, and I'll get back to why this is important. Okay, so I want to talk about a few things which we've been working on to help approach this problem. We started out thinking about the world primarily in a terrain-aware manner, and recently we started thinking about it's not just about terrains, it's about lots of other things. It's about geometry, semantics, affordances, and I call that open world navigation, so I'll talk a little bit about that, okay? Let me first talk a little bit about some of our early work on learning these visual representations. So we want to navigate in these urban environments. There are things like these paths and grass and bushes that you want to try to avoid or distinguish them at least, right? So how can you learn about these things, right? So what you can do is you can actually, for example, have a human demonstrate what it is to drive around in this world. And if the robot initially doesn't know anything about these terrains, this is what it sees, right? Okay. However, the robot can actually hypothesize using its geometric planner some shortcuts, these green paths that it could have taken. And these are rather interesting because I'm going to call these implicit counterfactuals. I would call them implicit counterfactuals because in these scenarios, for example here, right, the robot could have taken this shortcut as far as its geometric plan is concerned. But the human did not take it. So the human actually went out of their way to not take that shortcut. So there must be something different about it, right? So this is actually a very interesting piece of information. So what we say is that if you take a patch from this point on the path that's demonstrated, you take a patch which is the thing that the human's clearly trying to avoid, and there must be some difference between them in the representation space. We don't know what the difference is and why, but it's there, okay? The second thing, the second structure of the variance, the invariance that we want to induce is what we call viewpoint invariance, right? So there's a location in the world shown in the green box, and the robot's seeing it from two different viewpoints. That thing that's in the world is the same thing no matter what angle you're seeing them from, right? So because of that, the visual representation of it from the image patches from the two should align, right? So therefore, the difference between them should go to 0. So you just take these two ideas and put them together. You can essentially come up with what I'm calling a triplet constraint. You can convert it into a loss function, and you can go to town and do learning, right? So essentially, the idea here is that you take the patches from the anchor and dissimilar, and the difference between them in the representation space must be greater than the difference between the visual and the the viewpoint invariant locations by some margin delta, okay? All right, so this turns out to work quite well. Also, by the way, you can learn the cost function as well, because you essentially say the cost over the demonstrated trajectory must be less than the cost of the alternate. So I'm just going to play a video of this in action. I'm just going to pause it to explain what's going on. Left is RGB input. Bottom right is a false color representation of the environment. Different colors just mean different types of entities. They don't necessarily, I mean, there is actually a semantic mapping, but we haven't explicitly made that clear, okay? So, I mean, by and large, you can see that the trail shows up in a different color. The robot's able to follow the trail. At this point, I think our robots are quite good at following trails around wherever we've tested it. It's not a problem. But vision alone is not going to get you too far, right? So this is purely vision-based. And here's the problem with vision, right? I'm showing you 4 patches, okay? And let me ask you a question. Which of these are the same terrain and which ones are not, right? Anyone want to take a guess? One guess. No one's willing to brave a guess. Clearly, it's a trick question. Okay, so the trick question is that the 2 things in the middle are grass. This is what grass looks like in spring and fall in Austin. This is what grass looks like in the summer in Austin, and this is bushes and concrete. Now, clearly, you can see that there's some texture differences between them. But which differences in texture are actually important, right? Which one should you pay attention to, and which textural differences should you not pay attention to? Guess what? Vision alone will not tell you that. To actually understand this, we actually came up with this algorithm, Sterling, which essentially is an unsupervised learning algorithm. And the way this works is that the robots moving around in the world, the operator is just driving them around. And just think of 3 points in time, right? So at one point of time, the robot sees a patch in the future. In a different point of time, it sees the same patch in the future. Recall the viewpoint invariance. I have that same thing here. And while it's driving over it, you can actually record things like the torque, the joint forces, the impacts that the paws of the robot feels, and you record that as inertial, proprioceptive, and tactile responses, right? And what you can do is that you can take these 3 inputs, pass them through 3 different encoders, the vision encoders are the same, the IPT encoder is slightly different, and then you essentially say that all of these must be the same because they're representing the same thing in the world, right? So this is the same terrain embedding. How are we doing on time? Okay, we're running a little bit late. Okay, so I'm just going to summarize really quickly what we're doing. We're just trying to align Z1 with Z2 and Z2 with ZIPT all the way. This is your loss function, essentially. I leave it up to you to read the paper to see the details. But this works out quite effectively. You can actually automatically learn these clusters of different terrains in an entirely unsupervised manner. This is quite effective. On the right, we see some interesting behavior which we weren't expecting. The robots never actually encountered water, but it's actually at least able to visually distinguish from everything else. And we just had a prior that the cost of unseen things should be higher. So yeah, it just ends up avoiding it. This is, I would say, out of luck. There's nothing in our algorithm there which explicitly would have said that water needs to be separated. It's just an artifact of how the things separate out in the representation space. I'll talk about something later which might actually have more of this, this behavior automatically, okay? All right, so we're operating in these environments using visual representations. I want to talk a little bit about how we can handle deployment time changing preferences. So what do I mean by deployment time changing preferences? I'm going to show you a cartoonish scenario where, for example, let's say the robot's going from here and it's going there. And you can have 2 preferences. One is that you prefer the red brick over grass or the vice versa, right? Of course, you might not actually really have this preference change, but essentially between environments, you might have slightly different preferences of like this type of terrain is okay versus not, right? So how do you actually encode these changing preferences? So if you're using a manually specified cost function, you're probably used to changing numbers, and nobody likes changing numbers. It's really unsatisfying. You have to do many times, and it's really painful. What we came up with is essentially a way of taking in what we call a preference context, right? So what is a preference context? So we have the input images, right? And then what we do is that the operator essentially clicks on the image and says, this is better than that. This is better than this. This is better than that. So we get 3 pairs of preferences These are sparse. We don't do them extensively. We only give it a few number of these pairs. And then that allows the algorithm to generate cost maps. And as you can see, the C1 and C2 have inverted costs because the preferences are inverted. Okay? So how do we actually do this? So the way we do this is we essentially have a preference context encoder. We have a BV encoder for the images. And then we run a bunch of things. And then you get a cost map of the output. To train this, you actually need some very specific, you need a very interesting training paradigm. You want to actually have 3 desired properties. You want to have some realistic priors over the environment. So when no informative context is given, so when the preferences provided do not specify anything about something, like concrete, then you should revert to some realistic priors, right? So concrete's good, rocks are bad, and things like that, right? When the operator specifies something, when the operator clicks and says that rock is better than grass, don't question why, just trust it and take it, right? And third is that you want to be able to generalize to completely new terrains. You've never seen them before, but the operator might specify a preference with respect to them, and you want to actually do that, right? So how do we actually, yeah.
So let's say you have like a wall in front of you,
Yeah.
right? And so every option is bad. Is that like handled by this prior somehow? Or how does the preference work there when it's just kind of like?
When everything is bad, so it depends on like if everything is bad, is it there in a realistic prior or not? If it's not there in a realistic prior, you actually need not a pairwise preference, you need an absolute preference, which is like this is just bad, period, infinite cost, right? So that is not handled by this algorithm. We actually have some follow-up work where we want to extend this as you saw, the preferences are being provided in a pairwise manner. We're working on extending that to richer forms of preferences using absolutes and also like strengths of preferences. So I can talk to you offline about that, the second thing, yeah, okay? Okay, so how do you actually do this? I'm going to breeze through this a little bit since I'm running a little bit short on time. So the high-level idea here is that during training time, so during at test time, we don't actually have classes, but during training time, we actually do have classes in input images. So we have classes of different types of terrains, and we actually have hand-coded costs for each of these different terrains, and we have a nominal ordering, a partial ordering of these terrains. So given this set of data, what we actually do is that create a bunch of examples of preference context just randomly generated, consistent with this partial ordered preferences, and then a target cost map, and then you train the neural network with that. To actually do the second property, what you do is that you shuffle the preferences, and then you put them in the context, and you take that from there, right? And then finally, for the third property, what we do is that we generate synthetic terrains, just random textures drawn from a graphics library, and just replace them in your images and put context with respect to that, and actually ensure that you actually deploy them to that. So this works out actually quite effectively. I will just show you a few qualitative examples. So here's a scenario, completely out of distribution. We've never trained or seen this. So you're actually telling it that the colors are really hard to see over here. But essentially this stuff is preferred to, like this stuff is preferred to that. So it's actually staying on that kind of terrain a little bit more. You flip the preference and it actually goes down lower a little bit faster. And similarly, you can see like the preferences on the cutting the corner versus not, okay? All right. So this is how we actually, this is one of the ways we're thinking about how we can actually adapt to deployment time changing preferences, right? All right, I want to talk a little bit about handling multiple factors. So I spoke a little bit about handling terrain-aware navigation. In the real world, the world is made of more things than terrains. Here's a negative obstacle. I can't believe UT actually has this, but there's a walkway where on the right there is no railing, okay? Our robot can handle this scenario, by the way. There are actually things like crosswalks, where again we have complex, well, I don't know about complex, but it's geometry which is very hard to like generalizably model. We have things like foliage obstruction. Hey, fall does happen in Austin as well. It just happens in December. So we were Arthur was testing this and picked it up in December, and other curb ramps. So we can actually handle these scenarios. We have an algorithm which can do this, which we're really happy about. And the way we do this is that we go from RGB and sparse depth. We can handle different ways of sparse depth. We go to some form of perceptual abstraction. And then from there, we do the cost map, as I just said. So how do we actually do this, right? So can we just build an extremely large robot data set? That's the topic of town, right? Just build a large data set. We've done that, we've built this socially compliant navigation data set. We created a campus object data set. Arthur will tell you a lot about this. Lots of other people have built data sets as well, right? And there are companies which are working on gamifying data set collection. I will point out an anecdote that even humans have problems collecting data. So we came to a campus once, and Arthur found one of the Frodobots robots on his face because they're collecting data. I want to actually point out why data set collection with robots is a problem. So during development, you have access to some entities of interest, and you have access to some environmental conditions. And what happens is that during deployment, you're going to have different sets of entities, or there might be some overlap if you're lucky, and there'll be some environmental conditions. And ideally, if you have overlap of all of these, that's awesome. But the problem is you actually don't, right? So going back to our view of the world, what's different? The entities are changing, and the world conditions themselves are changing, okay? So here's a question. Can we somehow leverage large pre-trained models to aid in this transfer? So what do I mean by large models? Well, you've all seen things like Dino. They can generate pretty pictures from RGB images. These colors correspond to semantics, similarity, and so on, right? Here's a question. What does this big data bring in these large visual foundation models? I posit it does two things, right? First of all, it over a ton of data, it actually learns invariance to world conditions. If you have an entity E1, right, and if you're observing it with world condition W and world condition W prime, the encodings actually end up to be similar for all W and W prime. It's not necessarily true that this fully works, but actually the large vision models are actually quite robust in this manner. The second thing, this is really powerful, is that they learn semantic similarity. So if you have two entities, E1 and E2, and E1 is semantically similar to E2, they will actually, the embeddings then turn out to be similar. Why does this matter? So let's say I've given you a demonstration for one curb ramp. A different curb ramp, which might look quite different, will show up semantically similarly in that space. So these are really powerful properties to have. These are properties which would be very hard to get only using robot data set, right? The challenges, however, that we have is that we have over-segmentation with these large models. We have mismatched focus. They care about certain entities, and we care about different entities. And then there's computational costs, right? So to handle this, we came up with this algorithm CREST, with Arthur presented at RSS. This conference yesterday? Yeah, it was yesterday, right? Yeah. So you should go talk to him if you're interested in learning more. I will give you a short summary of how we do this. So recall I said that we're learning some perceptual abstraction, right? So what are these properties that we want to actually encode? So here are some ideas that we thought of that would be good properties to have. It's good to have some notion of the semantics of the environment. It's good to capture objectness, right? So what do I mean by objectness? The fact that a rock is different from a tree and so on. It's good to capture what's static versus dynamic and something about geometry, okay? So keeping these ideas in mind, what we came up with is a representation which actually creates three layers essentially. So you have an RGB cloud. What you can do is that you can use the LiDAR during training to separate out the static parts of the environment from the dynamic parts. And then what you can do is that you can actually project onto them the Dino features, right? And then after that, you can also extract the elevation map, which is all of the objects removed, right? So that's kind of what we do. I'm just going to give you a glimpse of this. I don't have time to talk about it. So essentially, we have RGB images. We do a lift splat operation and a BV encoding, and we actually learn a static decoder, a dynamic decoder, and an elevation decoder. We come up with a structured representation and actually work with that. Another key idea here is that what we're essentially doing is that we're taking internet scale data, using them to train a bunch of different foundation models, and using distillation and alignment using unsupervised robot data. So this is how all of these data pieces fit in. And then that gives us robot-specific representations, right? And very briefly, essentially what we're doing is that we use Dino to generate these semantic features. We use segment anything to actually say these different objects should be separated separately, and then we use depth infilling as well, okay? Okay, so that's how we come up with this representation. How do we actually learn this cost function? So the challenge with IRL is that, let's say you're moving around in an environment and you're demonstrating a path. So here's a path that the human could be demonstrating, right? And the human's trying to avoid these blue regions, okay? During deployment, it's very common for this robot to cut corners. I'm sure you've seen this. You've trained your robot and it cuts corners. What you really need to teach the robot is a negative example that going over the blue stuff is bad, right? But this is really hard. You can't actually do this in the wild, otherwise you'll destroy a robot. So what do we do? So what we do is that, what we do is that we use what are called counterfactual demonstrations. So you can think of these as scenarios where the robot hypothesizes alternate paths, and we have a procedure for generating alternate paths by pushing apart essentially multiple options. And then we just ask the human, are these other paths at all reasonable, right? And the way we do this is in this loop. So first you have these expert demonstrations, you run classical maxent IRL, you get a cost function, and then it enters essentially an active learning loop where you find divergence, you query for counterfactuals, and then you add that into your counterfactual IRL, which I leave for the full paper. But essentially what it's doing is that it's trying to separate out these counterfactual demonstrations from the on-policy demonstrations as much as possible. And this works out quite well. We've done experiments with running this with only 3 hours of demonstration data. I will just show one result, which is in the short horizon scenario, where we're deploying on different environments. These are, there are some environments which are unseen environments. The gray bar is the length of the path. The orange bar is how far we can navigate between interventions. We're a lot better than any of the other baselines, 5x fewer interventions. And just to qualitatively show you how some of this works, I'm just going to play the CREST video in the interest of time. So here's a scenario where it's actually negotiating these curb ramps. And one interesting property is that it makes corrections, but it makes very subtle corrections. It doesn't try to overcorrect or undercorrect, which I think is rather cool. And it's kind of like staying in the middle of these curb ramps. We didn't actually explicitly hand code any features for these curb ramps, but you get these things with enough counterfactuals and the right data. Okay. We've done a lot of extensive testing over 2 kilometer horizons and all, and it works well. We can also briefly say that you've tested with different forms of modality, and yeah, it works. Okay. All right, I'm running out of time, so I'm going to just quickly summarize what are some future directions. Here are just some thoughts. I could be wrong, but I have some hypotheses. So alignment via distillation, I briefly touched on it. I think it's going to be a good idea or a key way to leverage these large pre-trained models, including vision, language, and audio for robust open world navigation. Robotics requires integration of these physical interactions. We're not in the world of just vision alone. We can leave just the vision and language to non-roboticists, okay? Third, no single form of human input is going to be sufficient alone. We need to work jointly with demonstrations, preferences, counterfactuals, natural language, and others, okay? Right, with that, I will stop, and I'll take questions if you have time for any questions.
Thank you very much. So why don't we start the poster session, and then anyone has questions, why don't we do that during the poster session? So we'll be back at we'll be starting up at 4 o'clock, so come back a few minutes before then.